Now that we've discussed control flow, we can move on to procedure calls. So when we say the word functions, they're also known as procedures. Usually at the ISA level, we discuss them as procedures, versus at the high level language, we call them functions. They're commonly used to make code more modular, to make it easier to read, easier to maintain, and they're also used to remove redundant copies of code. So if we reuse some sort of functionality many times, we can just use a function instead of rewriting that code and putting it inside our memory. We provide functions in two separate ways at the C level. First of all, as the function definition. That includes a full description of the function, including the header and the content. So something like this. We have the type, the return value of the function, the return type of the function, then the function name, the arguments in the function, which each comes with the type of the argument, and inside of that, we put the code for the function. Or what we call a prototype, or just a function declaration. And that's an abstraction of the function, only providing the header or the interface. So here again, we have the same function type and function name, and the same list of variables, the header, the interface, but we don't provide any code inside. And so an example of that is, here's a function definition. We have int myfunc. That means we're going to return an int from myfunc. We get two variables, int a and int b. We have an internal variable that is called c, and we do some sort of operation and return something. Okay. But then we could have prototypes. So myfunc would be just prototyped like this: int myfunc, int a, int b, with a semicolon at the end, without providing the internals of the code. But it could be like int main, char foo, int star bar, so that's going to return a pointer, or void bar, which is not going to return anything. So what we have here is the type of value that will be returned. So when we have a return value, it should be of type int, and that's okay here because C is an int. Okay, we have local variables. So C is a local variable, which we'll discuss in a little bit. Its whole scope is only inside this function. We have the return value, as I said before. So whatever we write return C, that's what's going to be returned from the function and provided to the program that called it. Okay, we have the arguments that are passed by the caller. So A and B are arguments that are passed to the function. And we don't necessarily need to have a return value, and then we can use void as the function type. Okay, and when we have this, differentiation between the function definition and the prototyping, that enables us to separate the headers from code, and it's very often provided that way. So we'll get a .h file or something like that, which will just have the headers that we include them, but we don't have to have the actual code. So how do we call a procedure? In machine code, it's implemented by changing the control flow. So we learned how to use control flow for looping and for doing conditionals like if, but we can also branch to the place where the procedure is stored in memory. So we just change the control flow to the address of the procedure. And this is achieved usually in unconditional jump, because we don't need to ask if we need to meet some condition in order to jump to there. We're calling a function, so we unconditionally jump to there. The thing is that we need to return from whatever we did and continue running the program in order. So we need to store the return address. And this is also called linking. And therefore, in the instructions, we use the word linking. So RISC-V provides two instructions. The first one is called jump and link. And so it's called JAL. And that uses the J format to jump relative to the PC. So if you notice here, this is very similar to the U format. In fact, it's exactly the same, with the difference that the immediate is now shifted left by 1. Okay, and that's for the same reason we did it before, where we can do half-word addressing. We don't need to do byte aligned addressing. So something like JAL RA label, what it will do, it will change the program counter, so change control flow to whatever the program counter is, plus an offset, which is by the size of the immediate over here, shifted left by 1, which provides us 20 bits. That means we have plus minus 20 bytes from the current address. Okay, and it will also store PC plus 4 inside whatever we put over here for the return address. So it's actually, I guess we should call it RD, but in the ABI, we're supposed to use RA for that. So we're supposed to store the return address inside RA, and so that's going to automatically get the PC plus 4, which is the next sequential instruction. So we know that when we come back from this procedure, we finish running the procedure, this should be the next instruction to run. The other way to do it is jump and link register, which is the same thing as jump and link, but instead of using PC relative displacement addressing, it's going to use an absolute address. So here we have the address stored in RS1. So PC is going to get the immediate plus whatever the address is that's stored in RS1, and we're going to again link to whatever we stored over here in RD or in what we called RA. So that's register displacement addressing. Why is there a difference between them? So if we want to use this type of register displacement addressing, first we have to store in RS1 the address that we want to jump to. And as we saw, that can be by using 2 commands or something like that to store that. But if we just want to do something that we know that it has a pretty large distance, up to plus minus 20 bytes from the PC, from the program counter, we don't need to actually mention the program counter in here. It's implicit, and therefore we can get this long immediate and do this type of code that's relative to the size of our current compiled file. So how do we pass arguments to a function? They're primarily passed by using the argument registers. So in our ABI, we have defined 8 registers to be argument registers. They're called A0 to A7. If that is not enough for us, then what we have to do is push the arguments onto the stack. And I remind you that the stack is this private memory of each function. And so if we want to use more arguments, we will push them onto the stack before calling the functions, and that's how we'll get to them. So the argument can contain either data or a memory address. And if data is passed, this is what we call passing by value. If an address is passed, this is called passing by reference. And this is another one of those things, because it deals with pointers, that tends to confuse people who are just starting with C, and people who use something like Java or other languages love the fact that they don't have to deal with these pointers. But of course, when we're dealing with the real machine level, pointers are a very strong and important thing, and it really shows us and enables us to manipulate the actual internals of the computer. Okay, so what passing by value is that in the function header, we have a regular C variable, something like this, int square. We write here int x. So that's a regular variable here in the header. And what that means is that we create a read-only copy of whatever argument we're passing over to here, and that's what this square function will work on. It will work on a read-only copy, and it will not be able to change whatever we pass to that over here. We pass the return value through registers, usually A0 and A1. Those are the return registers that are defined by the ABI, or we can stick things on the stack. So let's see how this is going to work, passing by value. Again, our function header is going to have a standard variable, int x over here. And so when we go into our main, we define some local variables and so forth, but we said that k, our local variable, is going to be equal to calling the function square with the argument n. And we saw that n is equal to 5 over here. So what is going to happen here, inside, when we get to the function is going to make a copy of n. So it's going to call it x, and x equals 5. Then it's going to go 5 times 5 is 25, and it's going to return 25. This is going to be equal to 25, so it's going to be passed over to k. But we didn't change n. And same over here, n is going to get square of 5. We can actually pass, no problem, some sort of constant, because it's just going to make a copy of it over here, use that constant, and return it. That is called passing by value. Again, it's making a read-only copy and passing it to the function. The other option is what we call passing by reference. In this case, the function header receives a pointer, and therefore we can actually modify the actual variable because we get an address, and we can go and dereference the address and do things on whatever is happening inside. So, for example, this time we don't need to return anything by this SQ function. We can use it as a void. So void gets a regular variable x, which it's going to make a copy of, but it also receives a pointer to integer, which is called y. Okay, and then when we call the this routine, what we do is square n and the address of k. So we give it 5, and we give it the address of k. So 5 is just made a copy over here, and we do 5 times 5 is 25. But since we gave it the address of k, that means y is a pointer, and we say that the value that y is pointing to is now going to be equal to 25. And that's it. We return without returning anything. So whatever k was pointing to now, it's now equal to 25. Okay, so that is how we basically pass by reference. We're actually working on pointers, and we can make changes inside the actual function itself. So when we do procedure calls within the assembly code, we have this ABI that defines us different parts. So what we have is what we call state registers, which are the stack pointer, the global pointer, the thread pointer, etc. And they tell us things about the state of the actual machine right now. We have saved registers, and saved registers are these registers that we have to agree that a procedure will not change these registers. Whatever the caller put there, if the callee wants to use these registers, it has to store them. Okay, so these are saved registers, and they're called S something. Temporary registers, on the other hand, are these just, junk registers that the callee is able to overwrite. So if the caller, the procedure that makes the call, needs to have these as part of his state after it returns from the function, it better store them by pushing them onto the stack or putting them into a saved register. Okay, and there are additional volatile registers, which again are kind of like temporary registers, but they have certain usages. So RA, for example, is where we should put the return address. A0 and A1 are where we should put the return values, and A0 to A8 are where we should put the arguments that we pass. But these can be overwritten by the called procedure. Okay, when we talk about the calling convention, which we discussed last lecture, so RISC-V defines the calling convention that it has to have the stack pointer, the value that it had when entering the function, it has to exit with the same exact value. So that's really important because it's part of the state of the machine. Okay, the stored registers also, they are stored, so they must have the same value at the end of a procedure as they were with entering it. So the caller can be sure that the callee will not change the stored registers, or in other words, that the callee has to actually save the registers before it goes and plays around with them. And the other thing is that the address stored in RA is where the function will return to. Okay, and in order to ensure this, a procedure will always include something that we call a prologue and an epilogue that we'll see now. So to call a procedure, what the caller will do, this is the function that is the external function that's calling the procedure. First of all, it's going to place the arguments in A0 and A7. If that's not enough, then it's going to place additional arguments onto the stack. Okay. And not only that, it also, if it needs to save registers, for example, it's T registers, if it needs to use them after returning, then it knows that the callee may overwrite them, so it should save them as well on the stack or put them in other stored registers. Then it's going to call JAL or JALR, and it's going to put PC plus 4 inside RA, so the callee will know where to return to. Okay, then the callee comes and applies the prologue. So the prologue is done by a register, by a function. So the function doesn't need to know anything about the caller. It just needs to know that it needs to do several things in its prologue before doing its task, and then everything will work. So what is it going to do? It's going to allocate stack memory for the variables and stored registers. So basically, the compiler looks at the code and knows how many local variables it's going to need, and therefore it's going to allocate room for them. And it knows if it's going to write over some of the stored registers that it needs to replenish to the callee at the end, to the caller at the end. So it also makes room for them inside the stack. Then it's going to store any of these saved registers. So if S0 or S11, it needs to use them in some way, it needs to store them because it's going to it needs to replenish them at the end of the operation. And it's also going to store RA only on the condition if its function call is made. So if it's a leaf function, it doesn't call anything else, it's not going to overwrite RA. But if it's going to call another function, possibly that other function is going to overwrite RA. And remember, RA is volatile, so it better store RA so it can again put it back into RA after it returns. So let's see some code. So this is an example. It gets an argument G and H that are both ints, and it is not a leaf. This is not a leaf function because it's going to call SQR of one of those variables and then do something with it. So how is this going to work? And again, this is just an option. A lot of these things can actually be done in registers and not use memory, but I just wanted to show you how to use the memory. So this is the label that's saying where this function starts. So we start with this prologue, and what the prologue is going to do, it's going to first decrement the stack pointer. So the stack in RISC-V goes from top to bottom. So we're going to decrement the stack pointer by 8 because we need to store 2 words. Which words do we need? We need to store H because it's going to be used. And again, this is an argument, so it's volatile. And we need to use it after returning from square. So square might change whatever is in A0 or A1 or wherever it is. Whatever's in A1. So we better store it. And we have to store RA because we're going to be, again, calling square. And so square may overwrite, or will pretty much for sure overwrite RA. So we store those 2 things inside the stack. So that's why we needed to allocate 2 words over there, because we're storing 2 integer values. Okay. Then we do this function call. So it's going to JLR to square over here. Okay. And then it's going to calculate the return value in A0. So actually, what was pretty cool here, when we called SQR, because it met the ABI, it stuck its return value, which was, the square root or whatever, or something like that, or the square of G, it stuck it inside F. And so we know, and F is going, the return value is going to be in A0. So we knew it was in A0. So now what we might need to do is return F, which is going to be F equals F plus H. We need to put that in A0. So we just need to add H to A0. Where is H? H, we stored it onto the stack before, right? Because we wanted to make sure that we wouldn't overwrite it. So first what we did here is we popped the 8 plus stack pointer up into T0. And then we could add it, and that's doing that F plus equals H. So here now we have the return value in A0. Okay, so we finished running whatever we needed to run. This was our task over here, and now we apply the epilogue before we return. So what we need to do is, again, restore the state before we return to the calling function. So we're going to reload the registers that were saved on the stack, including RA. So we load word, stack pointer plus 4, which is over here, right? We stored it in stack pointer plus 4. We're going to return it into RA, and then we're going to deallocate the stack. So how do we deallocate the stack? We're going to increment the stack pointer by 8. That's over here. So now SP is returned to its initial value. Initially, we decreased it by 8. Now we incremented it by 8. Now stack pointer is back to its initial value when we made the call. And now we can do this JLR, jump in link register, and we're going to jump back to RA. Now look, the linking address, the linking register is just X0 because this is actually a jump. It's not a jump and link, but we don't have a jump command in RISC-V. We just use a jump and link with this kind of dummy return address. We don't need to actually store PC plus 4 anywhere because it's X0 over here. So now we can go over to variable scope, and variables in C have this thing that is known as scope. So local scope is when we have a variable that's defined within a function, even main. So we have void main over here, and we have function k that was defined inside. That's a local to the variable. And local variables, therefore, they are stored on the stack frame of the procedure. We said that each procedure, it receives a stack, including main. Main, again, is not a global. It's a procedure, so it itself has a stack, and this k will be allocated to be inside the stack frame of main. And when we return from that, we're going to deallocate the memory, and so these variables are going to die. K will die once we exit from main, if we ever exit from main in this case. Okay, global scope, on the other hand, are variables that are defined outside of functions. So, for example, this variable here, char a, that's outside of these functions, main or myfunc and so forth. So it's a global variable, and everyone needs to know about it. And therefore, there's a special area that is called the static data where it is going to be stored. So we have the global pointer that is going to be pointing at the beginning of the static data, and therefore we can just address all of the global variables that are stored inside here. And we also have something called static scope. So when we use the static keyword over here when defining a variable inside a function, what that means is that the scope of this variable C is local to this type of function. So anytime we call myfunc, it's going to be able to use the same variable C that was there before. And that's very useful. It's like a family of functions over here. Now, automatically in C, these types of static functions are initialized to 0, and we have a special area inside the static data that stores these type of static variables and initializes them to 0. But again, it's going to be inside the static data because at different places within different functions that have different stacks, we're going to be able to use this static variable, so we need to address it through the global pointer.